All right. Hi there for those of you watching the recording. We've got some web work questions here. 6.3 numbers 6, 9, and 10. So what do you guys think about this? Um, we've got some questions here about set difference, intersection, and union, along with some cross products, right? So what do you guys think? This first one here, true, false? Why would it be true or false? So what do you guys think about this first one here? True. Okay. What about the second? You think the first one's false. Okay, Sean, do you have a counterexample? It got fuzzy again. Uh-oh. Is it better now? Still messed up? Yeah. Okay. Is that better? Just
Yeah, you're sounding good now. I don't know what the difference is, but sometimes it's kind of fuzzy and sometimes it's not. I say it is false because that's what I got, and I did get this problem. I did it like a week ago now, so I'm not positive why. It'll take me a minute to come up with why that was.
Gotcha. That's fine. So there must be a counterexample, right? If it's false, where you give some values to A, B, and C, and then show that this doesn't work, right? That they're not actually equal. So if someone wants to come up with a counterexample, that's fine. How about this? And we can work on the second one at the same time. Do you remember if this guy's? Well, so you don't want to do a Venn diagram with a cross product because you can't really tell. There's not really a good way to draw a cross product in the Venn diagram. So you want to actually do set roster lists and see if and see if these things are actually equal, right? And you have to be a little bit creative about thinking about examples or counter examples as to how that would work. What you can see here is that if one is false, two should be true, I think, right? Because these should not be equal to the set difference is just intersection with a complement, right? One is true. Okay, so we're still arguing about this one. Okay, this one won't be equal, right? I think number 2 is true, and I think we can show that these aren't equal, right? Because if we do A cross B minus C, right, then that's going to be different than if we subtract off the A, right? So now the A is part of the set difference, but on the left side it's not. So maybe we can come up with, we are subtracting pairs, that's true. So can we come up with a counterexample where this left side is not equal to the right side? Or maybe we were incorrect. Maybe this one is false. Maybe they are equal. Okay, so you think these two things are equal? Okay. They should be equal. Okay, so y'all agree on that. Okay. Well, what about the third one? Third one's true. Okay, and what about the fourth one then? Fourth one's false. Okay. So in other words, you're saying that the cross product distributes over intersection and over, set subtraction, of course, which is the same thing pretty much, and union, but not symmetric difference. So it would distribute here on number 2, because we're saying that the non-equals, right? The not equals is false, right? So since we're saying not equals is false, we're saying, oh, it does actually distribute, right? Okay. And then this last one is actually doesn't work, you're saying. Okay. So why would that be? In this one, can you think of a counterexample? Okay, sure. So if it distributes over subtraction, it should distribute over symmetric difference. Well, okay, that's a fair argument. Is it true? I mean, we got a union and a subtraction here. So maybe that's going to mess it up somehow. I would just love if someone would give some sort of argument as to why any of these are true or false. That'd be great. What do you guys think? Like how, if this thing's true, how do we prove that it's true? If this thing's false, what's a counterexample? Well, I suppose while you're thinking, we can check our work here. Okay, so we got them all right. So that's good.
So I didn't specifically do like the algebraic proof, but once you have that the cross product distributes over the intersection, you can rewrite subtractions as intersections and show that the cross product, like algebraically do the proofs where you show that the cross product then distributes over those intersections and then brings back together so that it's the subtraction. And then once you've showed that, you can show that the cross product does distribute over the symmetric difference because it distributes over the difference.
Okay.
Does that make sense?
Yeah, it does. So you're saying if you assume that 1, or I guess maybe 2 and 3, right? If we know the answer is there, that the cross product distributes over subtraction and union, then it would distribute over this subtraction and this union.
Right.
I see.
And before you show that it distributes over subtraction, you could show that it distributes over intersection, and then a subtraction is just an intersection, so it distributes over that too, algebraically.
Yeah, I think that's a fair plan. So here, so let's let me turn my camera on here. Let's see if we can do a little algebration here.
As for proving that it distributes over the union and intersection, I don't know exactly how I did that.
Okay, that's fine. So let's stop sharing. Okay. Oh, and Lucas, you have an idea for how to prove that one. Well, maybe let's start with the first one before, we'll start at the beginning and work through. Okay, cool. So what did we have here? So we want to know, Lucas, you were talking about number 1, okay, which is intersection. So we want to say A cross B intersect C equals A cross B intersect A cross C. Right? You were thinking about union. Well, it should work either way, I think, right? So every element of A will be the first element of every pair. Every pair starting with A, there will be every B and every C. Okay. So let's do an example here, right? So if A has, 1, 2, 3, B has, A, B, and C has B, C, right? Or here, maybe we'll make the A's in common. AB and AC, right? Well, what's the intersection B intersects C? A, right? So on the left side, we would have 1A, 2A, and 3A. Okay, what are we going to have on the right? Well, now we'll have 1A, 1B, 2A, 2B, 3A, 3B, right? Okay, and then we're going to intersect with this guy here, which will be 1A, 1B, 1A, 2A, 3A, 1C, 2C, 3C. And what do we have in common? Well, we have all of the A ones, but none of the B or C ones. Those don't intersect. So what we get is 1A, 2A, 3A, and you can see that these guys are the same, right? Okay, so that's kind of a nice way of thinking about it. I think that's not a proof yet, but that's moving in the right direction for sure. Okay, we could probably do the same thing with union, right? If we wanted to have union here, then instead of just A, it would be A, B, and C were all in here, and then we would have those 9 results. Same deal over here. Okay, and then if we have that, then we can think about that symmetric difference, right? So we'll have A cross B triangle C. Okay, and let's see if we can do a little derivation here. Well, if we plug in the definition of symmetric difference, we'll have A cross B minus C union C minus B, right? Okay, so then from there, what are we going to get? Well, then we can distribute this A cross over the union. So we'll have A cross B minus C union A cross C minus B. Well, and then we can distribute those A's in to the set subtraction, right? So we can have A cross B minus A cross C union A cross C minus A cross B. Okay. And now what do we have? Does anyone see the last step? Okay, so the last step here, this just is the symmetric difference by definition, right? This one minus this one, union, right? The first one minus the second one, union, the second one minus the first one, right? Which means that's just A cross B, triangle, A cross C. And there's your little algebraic derivation, assuming that you have union and set subtraction distributive properties already. What do you guys think? Does that make sense? Okay, you're happy with that. Cool. Well, what about this original thing, this original proof, right? So we had like a pretty good idea. Well, we put 1, 2, and 3 and A, B's, and C's, and it all looked okay. What's the actual way that you prove one of these things? There's a method that we learned.
To prove set equality, you prove one set is contained in the other set, and then you prove the other set is contained in the one set, and you do that by picking out elements and showing that they're elements of both sets.
Perfect. A proof by elements, right? To show containment both ways. That's exactly right. Yep. So that's the strategy that you wanted to use here, as well as for the union and set difference. And then once you have those, then you can do an algebraic derivation like this one. Cool. Okay, so there's number 6. Let's move on to numbers 9 and 10. So here, actually, let me turn this off, that on. Okay. All right, so this is a similar sort of thing, but this is all about, the power set and how that works, right? Okay, so if A is contained in B, is the power set of A contained in the power set of B? True, okay. Oops, true. Okay, this next one. No idea. Okay, true. I got some trues here. Yeah, how about this one? False. Okay, can you give me a counterexample, Natasha? What specific sets can we set to A and for A and B so that that containment does not work? One and two? Okay, is that A or B, David? Or is that A and B? A and B, got it. Okay, so A just has 1 and B just has 2. Okay, so then what would be the power set of the union? Well, that would be the power set of 1, 2, which would be empty set 1, 2, 1, 2, right? Okay, that would be the left side of the power set of the union. Okay, so let's do the union of the power sets. Well, the union of the power sets is going to be the power set of 1, which will be 0 and 1. The power set of B will be 0 and 2, right? And so the union of those will be 0, 1, 2, which shows that, in fact, that first one is not contained in the second one. The second one is contained in the first one, so that one's actually true by our example, right? But this one certainly is false. Okay, and the way to actually prove these, again, is containment with proof by elements. And so if you want to go through an extended proof, you'd want to use proof by elements for that. Let's see if we're right. Looks good. Okay, any questions on that before we move on? Does that look good? Okay, cool. So let's do one more. All right, so now we got some other distributive possibilities here for the power set. So what do you guys think about these?
I think the first one's true.
Okay.
The power set of the complement is the complement of the power set.
Okay. Great. What about these next ones?
I said they were all false and I got one of them wrong, so I'm not sure.
Okay. And some people in the chat are saying this first one is false. So, and you said these are all false and there's only one that's true because you got one wrong. Okay, so which one is true out of all of these, do you think? Yeah, I think a simple example is a good way of doing it. A has, the elements 1 and 2, B has the elements 2 and 3. You can just run through and see if the example works, right? So it appears that power set doesn't really distribute over much stuff. And if we check answers, let's see here. Oh, we do get all false.
Well, because so I had said that the power set of the complement is the complement of the power set. Why is that not the case? That seems like it would be to me.
Yeah, so let's see if we can find a counterexample. So maybe for A, we can do the set 1, 2, right? Just so that, you try to make it as general as possible. Right? So you say, okay, well, the most general example is there's more than one thing in the set. So in that case, if you have, let's say that, and we do need to be aware of the universe here, right? So let's say that the universe is 1, 2, 3, and set A is equal to 1, 2, right? In that case, the power set of A complement equals the power set of the singleton set 3, which is the set of empty set and singleton 3. Right? Then instead, if we want the complement of the power set of A complement, well, first of all, what's the power set of A? Well, it's going to be 0, or empty set rather, 1, 2, 1, 2. Okay, and we want the complement of that. Well, that's going to be, it's first of all, the empty set's going to not be in the complement, right? So this is already going to be wrong. Right? What else is going to be in the complement? Well, but if not the power set, well, certainly the set singleton 3, but also anything else with a 3 in it. So 1, 3, 2, 3, and 1, 2, 3. Does that make sense? Yeah, you see it now. Yeah. So does the universal set not contain sets? No, the universe here just has the elements 1, 2, and 3, and A has the elements 1, 2. So if you want to think about it, as a picture, here's my universe. It has the number, 3 out here, and then the set A with 1 and 2 inside. Does that make sense? Lucas, does that make you happy? Power set of A is not a part of the universe. Well, the power set of A is a part of the power set of the universe, right? So I think here when we do these power sets, right, we're doing the power set of A complement, which would be the power set of 3, then the power set of A quantity complement. Yeah, now it makes sense. Okay, nice. Yes, that's the power set of the universe. That's exactly right, Haruka. Yep. And then the question is, we have the power set of A complement and then the power set of A quantity complement, and do those pick out the same parts of that power set of the universe? And they don't, right? This one has 4 elements without the empty set. This has only 2 elements with the empty set. So, so they can't be the same subset of the power set of the universe, right? They're different subsets of the power set of the universe. Does that make sense? People good there? Okay. Should we do another one of these, or I think we should. Yeah, let's move on. Yeah, I think that's a good thing to do. And Amber, you have some questions there, so let's move on to 7. Okay, 711 and 713. Okay, so let me stop this guy. Okay. All right, 711. Okay. You're not sure what it's asking for, f of s. Does it refer to the codomain of s? Not exactly. So f of s is the image of s under the function f, which is a subset of the codomain. Right? So what basically it's asking, if we take this region S and apply the function to it, then what new region are we going to get inside the codomain, right? So if S is open from 3 to 4, and then what we're going to do is take the absolute value of that and multiply it by 2. Well, the absolute value of anything in the range from 3 to 4 is just equal to itself, because these are all going to be positive numbers in here. So the absolute value doesn't do anything. Multiplying by 2 does something, right? So multiplying by 2 is going to stretch out the whole range from 6 to 8 instead of 3 to 4. Yeah, that's exactly right, Haruka. Yeah. So it'll be open on 6, closed on 8. Okay, and then what about the inverse image of that function over S? Well, in that case, now the absolute value is going to do something, because the output from the function is the range from 3 to 4, which means the input would have been either 3 to 4 or -3 to -4, because that absolute value can transform negatives into positives. If our outputs are positives, remember these are the outputs now because we're looking at the inverse function, right? So if the outputs are positive, the inputs to the absolute value could have been positive or negative, and they would need to be half as big, right? So we could have the open interval from 1.5 to closed 2, or we could have had open on -1.5 up to closed on -2, right? Okay, so let's see if we got that right. Oh, I did that in the wrong order. -2, -1.5. Okay, let's try that again. Put them in the right order. There we go. That's better. What do you guys think? Does that answer your question, Amber? Perfect. Good. Okay, so then let's try number 3. And you had a question here. So you said, the line goes off the screen. You can't tell if it approaches -11 or does it start at -infinity? Yeah, no. So this is not meant to be an asymptote. It's meant to just be. Oh, and yours is a little different. Okay. Well, this one is meant to be just a parabola. It's not meant to go to an asymptote at -10. Is your graph pretty similar to this, Amber, or is it pretty different? Because what I can do is I can let you share your screen. Oh, it's upside down. Okay, but it's pretty much the same. It's just upside down. Okay, cool. So I think in this case, I would say that this is just going to be a parabola. So this will go off to -infinity. So what's the domain? Cool. Okay. So what's the domain here? What inputs from the x-axis are going to give you a valid output? And so what are going to be valid inputs to this function here on the x-axis? Okay. -infinity and -1, both open, because, oh no, the -1's closed. Yep, you're right. Because here this dot is filled in. So we go -infinity all the way up to -1 closed, then 3 open to 6 closed. Yep, I agree. And then there's the other part of the domain from 3 to 6. Okay, so what about the range? What outputs can you get here? Good. -4 closed all the way up to infinity, which of course has to be open. Okay, let's see if we're right. Yep, looking good. I'm not sure I understand your question, Calico. Let me do this. Let me make it so you can share your screen. And I think if we see that picture, it'll be a little bit easier to understand. Okay, so Calico, I made you a co-host. Would you share your screen so that we can look at it? All right, perfect. And so you're wondering about that second part and how to use union, is that right, on the range? I see, yeah, your range has a
Yeah,
break.
I just didn't know how to do the union when there's just one point and not like an interval.
Oh, I see, for the line up
Yeah.
top on the first quadrant. Yeah, so I think you should be able to, and you can't just say from 6 to 6, that doesn't work. Can you do 6 to 6 closed? Like 6 comma 6 in there? Yep, that works.
Thank you.
Perfect. Yeah, you're welcome. Yeah, I think you also can do 6 inside of curly brackets, because what's an interval? Well, it's a set of numbers that go over the number line, right? And if there's only one number in your interval, then that's just going to be the set of that number. So Sean, I agree with you. I think that if you just did 6 in curly brackets, that would have worked as well. Yeah. Okay, cool. Any other questions for me? Questions on proofs, other web work stuff? Or should we jump into chapter 7? Okay. So thank you for bringing that up, Vivi. Yeah, a bunch of people emailed me. My apologies. I forgot to change the due dates on the collaborative proofs. So I just made it due tonight for last week's. So if you missed it or it got messed up, please do turn it in to the discussion forum. I changed that so it's open till tonight, and they will be due on Saturdays from now on. I said I would do that, and then I just forgot to change it. So I'm sorry about that. But everyone, I think, now should be able to turn it in. Yeah, you're welcome. Okay. Any other questions for me? All right. I do not grade collaborative proofs based on correctness. Yep, that's right. I just check and see if you've tried. If you tried, then you get full credit. Yeah, you're welcome. Okay, other questions? Alrighty. Well, in that case, let's jump into chapter 7. All right, great. So chapter 7 is all about functions. I don't know Grelling's paradox, Amber. Can you describe that to me? Or maybe I should just look it up. Maybe that'd be faster. Oh, was that the name of the heterological one? Is that called Grelling's paradox? I was not aware. Okay. Well, yeah. So is it a paradox, right? if is, you know, if I say, is the word heterological, right? Then I think it is a paradox, right? So of course, heterological means what exactly? Hetero means different, right? So what's different about what is that describing? Non-self-descriptive. Okay, so it's different than its own description, right? Okay, so if you're not being self-descriptive, okay, then let's do an example. So can you give me an example of a word that is not self-descriptive, that is heterological? Adjectives describe nouns, not adjectives. Sure. Okay, so maybe we would want an adverb. Those can describe themselves, right? What about the word lovely? Is the word lovely actually lovely or no? Like the way that the letters look, the arrangement of the letters themselves, right? Is that a lovely word? Yeah, if I write it in cursive, how about that? Right, is that lovely? Right, so that would be homological. Right, because the word describes itself. Right, this arrangement of lines and curves is itself lovely, just as the word is. Okay, so let's do one that's homological, that's different than its word. How about, do you guys have one? I have one, but let me see if you guys have one. Yeah, huge or big, right? I think big is even better. Big is only 3 letters long, so it's not a very big word. Same thing with huge. Huge is not a huge word, it's only 4 letters long, right? So that would be heterological. Long, that's another good one. Yep, yeah, I agree. Okay, so now we're thinking, is the word heterological, right? Yeah, so, right, exactly. So is this word different than its own description? Well, there are 2 possibilities. That could be either true or false, right? If heterological is in fact heterological, then that means then it is different than its own description, right? But I just said heterological is heterological. That means it's the same as its own description. So that doesn't work, right? And what if I say that heterological is false? Well, that means that it's not its own description, which is precisely what heterological means, right? But okay, so Amber, you're asking something a little different, though. It looks like it's an adjective. Adjective describe nouns, so it is heterological. I get it. It says adjective instead of a word in general. I see. Okay. Well, does that make it not work? Well, no, I think that's still okay, right? Because why? How is that okay, right? So this word big or huge, that's an adjective, right? Like if something's big, like a big dude, right? Then the dude is the noun and big is the adjective. So heterological is describing an adjective, right? So is heterological itself an adjective? I see. It's not, right? Because something that describes, well, but that's not really it, right? Like this is describing this word, right? The word big, you know, the arrangement of lines on this page, you know, with a B and the I and the G, right? That's a noun. That's a, a concrete object, right? This arrangement of ink on my paper, right? So heterological then, I would say, is an adjective that describes the noun big. Even though the word big is itself an adjective, we're not talking about the sort of the word big. We're talking about the arrangement of ink on the page when we use heterological to describe it, right? That's the description of it. So maybe that resolves your issue, Amber? Does that make sense or no? No problem, Seth. So Amber, does that more to think about? Okay. Well, do me a favor, Amber. Why don't you? Okay. So you looked online and some people, you found some people that agree with you. Okay, cool. So let's look. Oh boy, that's a hot mess. There we go. That's better. Okay, well, I can't look at the chat window. Sorry, guys. Yeah, monosyllabic, four-lettered are non-self-descriptive. Okay, so I agree that unspellable is not unspellable, right? Because it's talking about the letters versus the meaning, right? And so when we say unspellable, it's saying, hey, is this collection of letters spellable or not? Whereas we're not thinking about the meaning of this word. We're just thinking about the collection of the letters. And is that unspellable? No, it is not unspellable. It is totally spellable. So the word unspellable is spellable, and that's not a paradox. I agree with that. Do you guys agree with that? Does that make sense? Yes, okay. So in that case, yeah, we're being befuddled by ambiguities in the English language. I agree. It's the difference between the collection of letters that comprise a word and the meaning that comprises a word. And so the argument here is that the Grelling-Nelson paradox falls victim to that same distinction and in that way is no longer a paradox. Is that right? I'm just trying to go fast here so we don't spend too much time. But it seems like that's the idea. Do I have it? Pretty much. Okay. Yeah, so then the question is, are you using heterological as a noun or an adjective? And yeah, so, you know, I think that that's a great question. And if that's how you responded to the proof, then that's absolutely an accurate answer. I think if you just use the basic idea that we were saying before, where, you know, it's just if it is, then it isn't. And if it isn't, then it is. I think that's fine too. I think either, you know, I would be happy to give full credit for either interpretation here. Obviously, this issue about the nouns and adjectives is going a little deeper into the, you know, the areas that are problematic here with the word heterological, and that's fine. I think going either direction on this proof here, even though, you know, the point of these proofs isn't to get the answer right or wrong. That's not the idea. The idea is to construct, you know, a correct and complete mathematical argument. And whether that argument is, you know, is totally correct or not is not so much my concern. Yeah, so I'm happy to give full credit in either of those cases. Cool. Okay. Yeah, great. All right. So let me stop that. Cool. So let's talk about functions. Right. So chapter 7 is all about functions. What's a function? Someone describe it to me. Okay, it takes inputs, gives outputs. Good. What are the inputs and what are the outputs? Like what sort of object do the inputs come from and where do the outputs go? Good, and that's right, David, right? X maps to a Y. The X's are the inputs and the Y's are the outputs, but what kind of mathematical object is that? The inputs and the outputs, that is. Give you a hint, it's expanding on what we did last week. Yeah, they're sets, right? So a function is a relationship between two sets, right? So a function f from a domain X to a codomain Y, denoted f maps from X to Y, has two properties or two rules. Okay, so what are the two rules for a function? Okay, every X relates to a Y. And what about rule number 2? Maybe I should say at least one Y. How about rule number 2? Yeah, no two elements point to the same Y. So let me rephrase that just slightly. Every X, oops, every, if I can spell, every X relates to at most one Y, right? So you can't have two X, the same X pointing to two different Ys, right? Oh, and actually, Luan, that's different than what you said. So Luan, you said no two X's point to the same Y. Actually, that's okay, right? We just can't have the same X pointing to two different Ys. Yeah, parabola is a function, right? Passes the vertical line test, right? So Luan, what you were describing, two elements pointing to the same Y, that would be one-to-one, right? So we are going to talk about that today, one-to-one and onto functions. But you have to be really careful about which is the one and which is the two, right? And one of those is going to talk about whether or not it's a function, right? And the other one is it a one-to-one function, right? Let's do this. Let's translate these into logic, right? So how would I say, you know, every X relates to at most or at least one Y? Any idea how we could do the formal logic for that? Okay, for all X and X, there exists a Y and Y. Awesome. Such that what? F of x equals y. Perfect. Great. The second one's a little bit harder, right? Because for the second one, we have to think about three objects, right? We have to think about an x relating to a y and a z, right? So if we, so we say, if x relates to at most one y, here's what we don't want to have going on. We don't want to have one x that relates to y and z at the same time. So this is what I call an arrow diagram, right? Where this is the domain, here's the codomain, and here's the function f, which maps, which creates relationships or connections or maps between elements of the domain and elements of the codomain, or from elements of the domain to the codomain. So these little arrows, right? They have a directionality to them. So we're moving from left to right. So codomain and range are actually two different things. So the codomain is everything in this circle that you could map to, right? And the range is only the things that do get mapped to. So for example, if I had another element up here, W, right? So the range here would just be Y and Z, but the codomain would be W, Y, and Z. Does that distinction make sense, Amber? Perfect. Yeah, great. Okay. So, so if you have f of x1 equals f of x2, then x1 equals x2. Okay. So, yeah, that's a little bit more like one-to-one. What I want to say is if f of x equals y and f of x equals z, then what? So we have for all x in x, and also for all y and z in y, then if f of x equals y and f of x equals z, then y equals z. Very good. Y and z have to be the same. Here, y and z are not the same, and this is the bad thing that we don't want to have happen, where y and z are different. Right? So we stop that bad thing from happening by saying, hey, if we get a y out of one of these and a z out of the other one, then they have to be the same one. It has to be that if we have an x on the left mapping over to some y and z on the right, then those y and z have to be different names, but for the same point. I mean, you can have, you can say maybe this point over here is, a 4, okay? And you can say, well, y is, y equals 4 and z equals 4, right? What do you guys think? Any questions so far? Is what you said the same? Okay, so David. Okay, so let's see if it's what you said is the same. You said f of x1 equals f of x2. Well, so you have x1 and x2. That's two different items in the domain, right? Oh, actually, no, I'm sorry. F of x1 and f of x2. Those would be elements in the codomain. Pardon me. And that implies so so you would say f of y equals f of z implies y equals z. Oh, I think it is the same actually. I take that back. I think, oh, it's the opposite. Yeah, I don't think it's even the opposite. I think it's just different. So if f of xy equals f of sorry, f of y equals f of z, that means that you have y and z in the domain. So for your example here, you have a y and a z like this, right? And what you said is f of y equals f of z. Here's f of y equals f of z. Right? So really what you're saying is, these two things are the same. Yeah, so it is one-to-one. Yep, that is the one-to-one definition, right? So you're saying you got y, you got z, you're taking the function of those, which means y and z both have to be in the domain side. And what you're saying in the codomain side is, okay, well, after you apply the function to those two objects, you get out the same thing, right? And whether that means that y equals z or not is saying something about the arrows in the domain rather than up here, the function definition is about the arrows in the codomain. Yeah, so I think it is different. Yeah. Yeah, you're welcome. Okay, so one more point here. If every x relates to at least one y, and every x relates to at most one y, how many y's does every x relate to? 1, right? Every x relates to exactly 1 y. Right? If you take rules 1 and 2 and combine them, therefore, every x relates to exactly 1 y. In terms of our picture, what does that mean here for our little function diagrams? What is that saying about the arrows, how they work? Good. Perfect. Every x has exactly one arrow going out. You can't have anything with 2 arrows, and you can't have anything with 0 arrows coming out, right? So this, if I had, a and an x and a b, right? And here's my function diagram. Well, this a in the domain is breaking rule number 1, right? There's no arrow coming out of a. The x is breaking rule number 2 because it has 2 arrows coming out. And this b is following the rules, right? Any questions there? Does that all make sense? Okay, so what would be the range in this particular, for this particular function? Although it's not a function because it's breaking the rules, but if we were to think of this as a function, right, what would be the range? Y and Z, right? Those are the things getting mapped to. W would not be included in the range, right? And the range is also called the image, right? So the range of f is just a different word for the image of f. These mean the same thing. Okay. There's also the inverse image, right? So what's the inverse image or pre-image in this particular situation? X and B. It's the things that map to the image. That would be the pre-image or inverse image, right? And what maps to Y and Z? Well, X and B do, right? So that would be the inverse image or pre-image. Okay, any questions there? Let's see if we can use the formalism to define those, right? So if I have, just come up here. So if I have this situation, okay, so here's 1, 2, 3, and 4, mapping to A, B, and C. Okay, so the range or image is what gets mapped to. Now, how would I describe that using the formalism? All right, so I've got set X, the set Y, here's my function F going across. The pre-image equals the domain when we have a function. If we don't have a function, then the pre-image is not necessarily equal to the domain. Yeah. So next week when we do relations, a relation is just like a function, except it doesn't have to follow the rules. So for those relations, then the pre-image will not necessarily be the same as the domain, but it will, the domain and pre-image will be the same for a function. Yeah. Okay, so how can I define this range and image situation? Okay, so the range is the set of y in big Y such that there exists some x in X where f of x equals y. It's the set of objects in the codomain that get mapped to by some element in the domain, right? And what about the pre-image or inverse image slash inverse image? Well, that's going to be the set of x's, the set of x's in X such that there exists a y in Y where f of x equals y. So the same basic idea, you just swap the x's and y's, right? And if we have a function, then this set, right, is always going to be everything in the domain, right? Everything maps to something. If we're doing a function here, right, there has to be at least one arrow coming out of every domain element, right, when we have a function. So this would just be equal to the domain when f is a function. Yep. Any questions on that? All right. So we've done some arrow diagrams. We've talked about domain and range and image and pre-image. Let's see here. Okay. So let's do some examples. Let's talk about some examples of functions, right? So if we said, you know, if we had f goes from the power set of the set ABC to the naturals, right? Where f of p equals the size of p, right? Where, you know, where P is some element of the power set of 1, 2, 3. Then let's draw an arrow diagram, right? So I'm going to have two circles. What's the contents? What's the name of the circle on the left? What's that called? The domain, okay. And in this particular case, the domain equals the power set of 1, 2, 3. And on the right is the codomain, which is going to be the naturals. Okay, so let's list these out. So what do I have here for the power set of 1, 2, 3? What are the contents of my domain? Very good. Except for 1, 2, and 3, we'll have A's and B's. But yeah, you got the right idea, Nathan. So we got empty, A, B, C, A, B, A, C, B, C, and A, B, C. Right? Okay. And over on the right, what's going to be in there? So for the natural numbers, yeah. So what's going to be contained in this circle? Not quite. So it's not going to be the same as the left side, and it's not going to just be 9 digits. It'll be more than that. What are the natural numbers? Who remembers? Saying the codomain just is the natural numbers. 0 to infinity. Perfect. Right? So we got 0, 1, 2, 3, 4, yada, yada, yada. Bunch more numbers that, they keep going down forever. Okay, so now let's do some mapping, right? So the empty set, what we want to do is we want to find the size of that and then map that over into the codomain here, right? So what's the size of the empty set? 0. Perfect. Okay. How about the size of A? 1. And then B or C, are those same, different? Same. Okay, good. So we got 1, 1, and 1 for A, B, and C. Okay, how about the next ones? 2. Okay, so for A, B, AC, and BC. Those are all 2. And lastly, ABC? 3. Perfect. Okay, and that's it. There's our arrow diagram. What do you guys think? Questions? Oh, I totally did it wrong. I see. That should be A, B, and C. Sorry about that. Much better. Thanks, Haruka. Now it's consistent. And this one's wrong too. A, B, C. There we go. That's better. Helps to be consistent. Sorry about that. All right. Other questions? Okay, cool. So let's do another example. So here we've got a Boolean function And for our Boolean function, okay, what should we do? So it looks like here we can add up all of the, in your book, they're adding up all of the inputs and then seeing if it's the result is even or odd. Okay, so first of all, a Boolean function has 0, 1, set 0, 1 for inputs and outputs. So a Boolean function, f, and we're just doing, looks like we're just doing single output functions here, right? So the inputs, the domain, are going to be some cross product of 0 and 1 in n dimensions mapped to a single output of either 0 or 1. Right? This little n up here is an exponent, sort of like, so for example, if I had R2, that would equal R cross R, right? Or R3, that would be R cross R cross R. And it's an exponent because you're multiplying here. Really what you're doing is a cross product, but it's sort of like multiplication, right? So if we had, if n was equal to 3, what would be the inputs to our function in that case? If n was equal to 3 here. Good, 0, 0, 0 up to 1, 1, 1, right? So our inputs would be, well, let's draw it out, right? So let's say that we have, you know, f goes from 0, 1 cubed to 0, 1, where f of x, y, z equals x plus y plus z mod 2. Okay. Now, in that case, we've got our domain and codomain. Our codomain is going to be easy. That's just 0 and 1, right? Our domain is going to have how many objects inside? If we're doing 0, 1 cubed. Yeah, 8 of them, right? Because it'll be the set 0, 1, 0, 1, cross 0, 1, cross 0, 1, which is going to leave us with 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and lastly 1, 1, 1. Okay. So let's put in the mapping, right? So where's this first, our 0th element going to map to? Zero, okay. How about this next one? One, okay, next one goes to 1. How about this one? 0, 1, 0. One, perfect. Okay, next one. 0, 1, 1. 0, okay. 1, 0, 0. 1, okay. 101, 0, 110, 0, and lastly 111 goes to 1. Perfect. Okay, so there's your error diagram for that one. Questions, comments? Okay, so let me ask you a question. What's the inverse image of the set 0? Everything with 2 1s. Okay, well, that's part of it. There's one more besides that. And with the all zeros, right? So the inverse image is going to be, first of all, a set. And inside of that set, we'll have triples, including all zeros, and 0, 1, 1, and 1, 1, 0, 101 and 1, 1, 0. So 101 and 1, 1, 0. Beautiful. Okay. What would be the formal definition of this guy? Well, the inverse image or pre-image of some set in the codomain. So maybe I'll say S. Is equal to what? Well, it's equal to, should I do X and Y? I don't know. I'll just use S and T. Is equal to I get it. Okay. Is equal to the set of D's in my domain such that f of D is an element of S, where S is a subset of the codomain. Well, Haruka, it doesn't have to be everything. If you're talking about the inverse image of the whole codomain, right? In that case, you're going to get out the whole domain as your answer. But if you have the situation S where, for example, we only have a subset of the codomain, we only have 0, but not the 1, then the inverse image need not be the entire domain. It could just be a part of it, right? That's what I'm saying here. It's all the things in the domain that map to the S, right? Or, just as an example, here's my codomain, here's my set S, right? Which is a subset of the codomain. And these guys are going to be the ones that map to it, right? So those ones taken together, those would be my inverse image of S. Does that make sense, Haruka? And everyone else, anyone else have questions on that? Okay, cool. So I think this is a nice place to take a break for a minute. Let's take 10, and then we'll come back and do some practice problems from 7.1. All right, so I will see you soon. Okay, so let's do a couple more examples from section 7.1. I've got one here where we have domain X and codomain Y. The domain X contains 1, 2, 3, and 4. Codomain Y, A through E. Okay. and we have a mapping list. 1 goes to A, 2 goes to A, 3 goes to A, and 4 goes to D. Okay. And we've got some questions here. So if capital A, this set, equals 2, 3, set B is, oh, sorry. Yeah, B equals the set A. C is the set BC. All right. Oh, I see. I did that wrong. Okay, let's call this one C. Sorry. Let's see what I did. C and D. Okay, so there's C and D. Great. So we're going to find the following objects. G of A, G of X. Oh, and this function is called G, by the way. So G of A, G of X, G inverse C, G inverse D, G inverse D, and G inverse Y. All right. Perfect. So let's start out with G of A. So what is this question asking, first of all? Can you describe it to me? G of X, not exactly. Nope, not quite. So A is a subset of the domain X, right? Yeah, the question is what subset of the codomain is mapped to by 2 and 3? So so David, I guess I would say what letters do 2 and 3 map to in this particular case, right? So what do you think? Just A. Good. So it's the set containing the letter A. That's what gets mapped to by both 2 and 3. Okay, so how about G of X? So what would be in there? A and D. Very good. Okay. How about the inverse image of the set C, which contains only the letter A? 1, 2, and 3. Good. How about the inverse image of D, which contains B and C? 0. Yeah. So I think, Luan, you mean the empty set? Is that right? Yes. Perfect. Very good. Because if you take B and C, that's what D has in it, B and C, you say, hey, what maps to B and C? The answer is nothing, right? Nothing maps to B or C. Okay, and how about the inverse image of Y, the entire codomain? X, the entire domain, right? And this will always be true. If you take the inverse of the entire codomain, you get the domain. That's always true anytime you have a function, which of course G in this case is a function. And maybe that's what we should talk about next. Can you guys give me an example of something that's not a function? Well, x equals y squared, or y equals the square root of x. Okay, so which I think is, you guys are sort of saying the same thing, right? So So how should we do this, right? So what should our domain and codomain be? Well, if it's the reals, I'm going to have a hard time drawing it, right? Because there's an infinite amount of numbers in the reals. So can I make this a little bit easier to draw? Okay, so that's a lot less, but I still don't want to write out 17 numbers in here because there's not a lot of room. So what's a sort of a bit smaller amount of numbers where I can still get across the idea of why this is not a function? Okay, -1 to 4. How about I do -3 to 3, right? So I just have a few more negatives in there. So over here on x, I'll have -3 up to 3. -3, -2, -1, 0, 1, 2, 3. Okay, and what should I have over here for my codomain? Maybe should I do the same thing? Should I just have those same numbers for my codomain, or should I do something else? 0 through 9. Okay, I can do that. So oops, ran out of room. There's 9. Okay, so what is -3 going to map to? Nothing. Well, then I don't think I had very good options here, right? Because I want x equals the square root of y. Is that right? Or sorry, y equals the square root of x. I think I did that backward, didn't I? Yeah, you said y equals the square root of x. Sorry, I did that backward. Y equals the square root of x.
So just to clarify, you were looking for something that is not a function, right?
Correct, not a function.
Okay, so if -3 doesn't map to anything in the codomain, that makes it not a function, right?
Correct. Yep.
And then there's also the thing where 2 will map to both. Well, I guess if we had gone like -9 to 9, 2 will map to both +4 and, or I'm sorry, maybe I have this backwards. Square root.
Yeah, positive.
We did the domains a little weird, didn't we?
Yeah, positive root 2 and negative root 2 would be what 2 mapped to, right? Yeah, so
right. There's 2 outputs for the 1 input.
Yeah, so I think that maybe what we should have over here, let's try this one more time, right? I think that what we should have over here is like, 0 and 1, those look okay. And I'm never going to get it mapping to oh, am I going to get negative numbers as the output? Yeah, I guess I am, right? So really what I should have had, let me try this one more time. So I've got x, -3 to 3. And over here in my codomain, well, I'm still going to have -1, 0, and 1. I think I should also have √2 and negative √2, and then √3 and negative √3. And I think that'll cover it, right? So what is 3 going to map to? Let's go bottom to top.
So then 3 maps to both positive square root of 3 and the negative square root of 3.
Good, because you could square either of these guys to get out 3, right? Okay, how about 2?
Same deal, maps to positive square root of 2 and negative square root of 2.
Perfect. Okay, and then 1, same deal, right? 1 will map to 1 and -1. What about 0?
0 maps only to 0.
Only to 0, good. And then what about these negative numbers?
Don't map to anything.
Don't map to anything, right? Because those would have to be complex numbers or imaginary numbers, which we don't have those in our codomain, right? So this breaks both rules of functions. We have some things that don't map to anything and some things that map to multiple things, right? Okay. Any questions about that? Does that look good?
I do have one thing that I wanted to ask about that was on the web work.
Mhm.
I forget which question it was. Let me see. I wrote it down here. 7.1.7. I think it's sometimes the notation with this gets kind of sloppy.
Okay.
It said that the square root of something was a function, and I think it meant when it didn't put the plus minus in front of it. Yeah, so it says that number 1 is a function.
Ah, okay. So
When if the inputs n are integers, then it should map to 2 different things. I think it's missing like a plus square root or something like that in like the notation.
Okay.
That symbol means principal square root. I've seen it used both ways.
So it looks like what their meaning is, they just mean that only the positive output will be considered in that case, which it's kind of silly. But well, no, that's not right, because even if, well, no, that is right. Yeah, because you're squaring these and adding 5. So underneath the root's always going to be positive, right? So you'll never have to worry about complex numbers. But then it might be a plus or a minus f of n, that when you square it gives you n squared plus 5. So I think it's just being a little tricky. So I see. I think you have a valid concern there.
I just wanted to point it out because I ran into it and I said that was false, and
Yeah.
or I said it was yes, or no, I said it was not a function, and it is a function because that means just positive. So I just wanted to point it out.
Yeah, no, thank you for doing that. So be careful about this one. Even though really it could be positive or negative, it seems like web work is only thinking about the positive version. Yeah. Okay, cool. Other questions? Okay, so let's do one more example from your book of something that is not a function, right? So, okay, so let's think about a function. Let's have some room in here. Okay, so let's think about a function h from the rationals to the rationals, where h of m over n equals m squared over n. Okay. And I claim this is not a function. Now, why would that be? Good. 1/2 and 2/4 are the same thing, but they would map to different outputs, right? 1/2, h of 1/2 would be still 1/2, but h of 2/4 would be 1 over 1, right? Well, it would be 4 over 4, which equals 1, right? So we would have h of 1/2 gives you out 2 distinct outputs, which is not, that violates the first rule of functions, right? Yeah, very nice, Lucas. Does everyone see that? Any questions there? Cool. Okay. So there's a couple examples of non-functional functions. Some of them that break the rules, right? Okay, so let's move on to one-to-one and onto. Get some more paper. All right, perfect. So what does it mean to be one-to-one or onto? What do you guys think? Okay, one-to-one is where each x corresponds to a unique y that no other x corresponds to. Perfect, right? So if we've got function here, so let f be a function, f maps from x to y. Okay, f is one-to-one if and only if for all x1 and x2 in X, f of x1 equals f of x2 implies x1 equals x2. That's perfect. Right? So there's the formal way of saying it. And in other words, in English, as Sean said it, is perfectly right. Each x corresponds to a unique y. Okay? So can you give me an example of a function that is one-to-one and an example of a function that's not one-to-one? Okay, y of x and sine of x, those are both one-to-one, but y equals x squared is not. Or David, did you think sine of x is not one-to-one? Sine is not. Okay, perfect. Okay, so why is that? Well, for one-to-one, what kind of a test can we do to see if a function is one-to-one? What's a quick test? You can even do it in your head. Horizontal line test, very good. So if I have this situation, y equals x, and I do a horizontal line through here or here, and that horizontal line is only going to intersect the function at one location, right? But what if I do sine of x? Right? And then I do a horizontal line. Well, this is going to intersect the function at many locations, an infinite number of locations, in fact. So this is not one-to-one. Same thing with x squared. If we do our parabola here, we do a horizontal line through it, you can see there's two intersection points. So that would not be one-to-one. Okay. Question?
Yeah, so I get that you can draw a sign like that, right? But like sine is defined using like triangles and hypotenuses and stuff. Is it fair to say that it's it's 1-to-1 when you're in like a certain domain, but not in others. Is that how you would talk about sine? It's just such a weird function. That,
Sure. Yeah. And just to make it a little bit easier, let's do the same thing for x squared, right? If I am considering the function x squared, how can I make this function 1-to-1?
so you could change the domain to just have positive x's.
Yeah, exactly. Right. So this is not 1-to-1 when the domain, when big X here, that's the domain, is, for example, the real numbers, but is 1-to-1 when X is just the positive real numbers, right? Because if I just don't have this whole side of the graph, right, because my inputs start right here, then it'll be 1-to-1. Same thing here. We could have the sine is 1-to-1 if, you know, is 1-to-1 when the domain is the interval from negative pi over 2 to pi over 2. Right, because here would be negative pi over 2. Here would be positive pi over 2. Right? And so, yeah, so you can see there that, you know, if we limit it to just this interval here, then it certainly is 1-to-1. It's when you start expanding out from that, right, that you start getting double intersections on your horizontal line. Cool. Okay, so that's 1-to-1. Any questions about that? Does that look okay? Okay, so what about onto? So F is onto if and only if what? So what do you guys think about onto? Okay, every X maps to a Y, almost. Yeah, so Lucas, you got it. Every Y has an X that maps to it, right? So for all Y in Y, there exists an X in X such that f of X equals Y. Very good, right? In other words, every codomain element gets mapped to. Okay, so of these functions up here, we got linear function y equals x, a sine function, and x squared. Which of these is onto and which one is not? So is a vertical line onto? Yes, a vertical line would be onto. Mm-hmm. Wouldn't be a function, but it would be onto. So that begs a question. Let f be a function. That function is 1-to-1 or onto, right? So can you have an onto thingy that's not a function? No, you can't. By definition, an onto thingy has to start out as a function, and then it might also be onto, right? So a vertical line actually couldn't be onto because it's not a function to start with, right? It doesn't pass the vertical line test, right? So, so Sean, you had the right idea, but it's the technicality in that definition that kind of messed up your argument there. So hopefully that makes sense. Sine and parabola are not onto. Okay, good, right? Oh, every time you try to come up with a function that was onto, you come up with things that aren't functions. Okay, so so onto in terms of okay, so tangent is not one-to-one, but it is onto. Yes. The inverse tangent, because tangent looks like this, right? That's tangent. Yeah, so you needed inverse tangent, which looks like this. That's tan inverse, right? So that would, well, yeah, that one over the whole domain. Oh, wait, no, I'm sorry. No, David, you had it right the first time. Nope, my bad. Yeah, because these things get repeated. So really what I'm talking about for tangent looks like this. Right? And so that's tangent, which is onto because it goes all the way up and all the way down, but it's not one-to-one because it fails the horizontal line test. Doesn't matter that they're undefined at plus or minus pi over 2. What you could do is you could just define them to be 0 at that point at the asymptotes, which is not really accurate, but you could define it that way, which would make it a function in that case. It wouldn't be tangent anymore, but it would be a function that was almost tangent, right? And then you would have a function that was one-to-one, but, sorry, not one-to-one, but is onto. What do you think? Does that make sense?
So to write something like that, you would have to do like f of x equals tangent of x so long as x does not equal some multiple of pi halves.
Yeah, exactly.
Yeah, okay. And 0 if it does. Okay.
0 if it does. Yep. Yeah, exactly. I think a little bit easier way to do that would be if you just did a cubic function. So if you did something like this, right? That would be a cubic polynomial function in x. So that obviously would be onto because, so what does onto mean in terms of these graphs, in terms of these images here? Well, it means that everything on the y-axis is covered, right? You can go up and up and up forever, right, on one side, or you could go down and down forever on the other. And every possible y you can pick all the way up and all the way down will have somewhere that if you draw a line across, it'll hit your function somewhere, right here, right? That's what being onto means. So you were right to say, okay, well, sine of x would not be onto y, because if I come up here and I have, y equals 2, right, here's 2, and I look and see, well, does that touch my function anywhere here? No, it doesn't. Right? Same thing here. So what would be an example of a point on f of x equals x squared that would show that the function is not onto? Which y does not have an x that corresponds to it? Yeah, anything negative, like -1. If I come down here to -1, right, there's nothing, there's no x that maps to -1 because the function doesn't reach down this far, right? Now, if you wanted a function that is onto but not one-to-one, I think if you did this cubic function like that, that would work. Let's go on Desmos for a quick moment. and see what kind of equation that would look like, just so that you get an idea for how to make that line. I think you just subtract off a linear term. Y equals x cubed minus x. There we go. What do you think? All right, so now if you draw a horizontal line, just right down the x-axis, you'll hit multiple points. So it's not one-to-one, but it will cover the entire y-axis as it goes up on the left and up on the right and down on the left. Yeah. Any questions there? Does that make sense? All right. So what about a function that is not onto, but is one-to-one? Can you think of one of those? So not onto, so there's some part of the y-axis that doesn't get covered, but it is one-to-one, so it passes the horizontal line test. Any ideas? Ah, the natural log. Not exactly, but you're on the right track, Sean. So the natural log actually goes up and down the entire way on the y-axis. Arctangent. Okay, so again, the inverse tangent situation, that would be, that's almost, I mean, again, with if you get rid of the exceptions, right, that would almost be one-to-one. Yeah, so Luan, I think that's the right idea. Absolute value wouldn't work. That's not one-to-one, but e to the x looks like this, right? So here's e to the x. Right? Now this would be one-to-one. It is not onto because of this situation right here. But it is one-to-one. So you can draw these horizontal lines. Okay, cool. That's a good one. Any questions about that? Does that all make sense? Okay, so how would you prove this? How would you prove that y equals e to the x is not onto, for example? Good. There's no x for y equals -1, right? So there's -1, right? And we would say it is not the case that there exists an x in x such that f of x equals -1. So not onto. It's a quick proof, one-liner, right? Good. Alrighty. Moving right along. Some stuff about laws of exponents and logs. Okay, fine. Let's talk about a bijection. Okay, so first of all, let me throw another little bit of vocabulary at you. A function is one-to-one. That's called injective. And onto, that's called surjective. There's just some vocab. Right? And if a function, or I should say a function, is bijective, two kinds of jective, right? Bi means two, doubly jective. If and only if it's injective and surjective, which makes sense why it's doubly jective, doubly jective, right? Bijective, because it's injective first and surjective second. So if it's both, it's called bijective. What does that mean, bijective? Like in terms of the arrow diagrams or these sort of graphs that we've been drawing. What does it mean for a function to be bijective? It's one-to-one and onto, sure, but and you're right. But in terms of like the arrow diagram, there's an equal amount of x's and y's. That's true. Hits y everywhere only one time. Okay. AKA every codomain element gets mapped to exactly one time. Okay, so it's kind of like the function definition, but for codomains instead of domains, right? Which, if every codomain element gets mapped to exactly one time, and every domain element maps to exactly one thing, right? Then that means there's a one-to-one correspondence, right? Each domain element corresponds to exactly one codomain element and vice versa, right? Which means that the number of domain and codomain elements must be equal. Yeah? So for example, let's do Jad's example, x cubed, right? So if I have, here's my x, here's my y, I have -2, -1, 0, 1, and 2, right? And I have x cubed is my function, right? Okay, so what's -2 cubed? So what are my answers going to be here? Okay, -8. How about -1 cubed? -1, 0, 0, 1, 1, and 2, 8. Perfect. And each one of these guys maps directly across to its buddy, its corresponding element, right? And so the arrow diagrams for bijective functions are usually pretty boring, right? I mean, maybe these guys could be mixed up, like out of order, so the arrows sort of like cross, each other or whatever. But really, as long as you can put these guys in some sort of reasonable order, the arrow diagrams here are always just going to be really boring. It's just going to be all the arrows going directly across, right? Which is to say, right, that let's say it a little bit different way, right? So there are two function rules, right? The function rule is that each domain element has to have at least and at most one arrow coming out, right? I'm saying that the same thing is happening for the codomain here to make a bijection. So what are injective and surjective saying about the number of arrows for the codomain elements? So what is injective saying about the codomain elements? It's 1-to-1. Okay, but what about the numbers of things being mapped to or doing the mapping? Okay, 1, true, but at least 1 or at most 1? Not both. Bless me. So there is one thing happening, that's true, but is it at least 1 or at most 1? Let's do an example, right? So this situation is not injective. Right? That's not injective. So what situation is injective limiting out? What's not allowed? Yeah, more than 1 is not allowed, right? So injective is saying at most 1 element maps to a domain element, I guess. Domain maps to every codomain element. Right? Because we can't have more than 1. We can't have this situation. So at most 1 domain element maps across. Okay, surjective is saying that this thing can't happen. Right? This one is the problem here, right? Surjective saying at least 1 domain element maps to every codomain element. So do you see how these are just like the rules for a function, right? Except they're talking about the codomain instead of the domain. But the idea of these rules is exactly the same. Yeah. Any questions about that? Does that make sense? Okay, you thought injective can't have 2 arrows coming out of the domain, not into the codomain. Can you say that again, Jad? I'm not quite sure what you mean by that.
Like one X value cannot equal to 2 Y values.
That's part of the rules of a function. So this situation.
Okay. I mixed it up.
Yep. So this situation right here, this makes it not a function. It has nothing to do with 1-to-1. Does that make sense?
Yeah. I mix it up. Sorry, my bad.
Okay, cool. David, you say, what determines if the inverse image is a function? Beautiful question. What's the answer? In what situation is the inverse of a function, and when is it not? Yes, that's right. If it's bijective, which means both surjective and injective, If you're both, then you're bijective, okay? Exactly in the cases when a function is bijective, then the inverse of that is a function. Because what would happen if you weren't, right? Well, if you had this situation where you're not surjective, then the inverse is just going the other way, right? So the function maps this way, the inverse function maps that way. So when would mapping that way not be a function? Well, if there's no arrow coming out of one of these, which means that your original function was not surjective, or if there are two arrows coming out of one of these, which means your original function was not injective. So in order for the function inverse to be a function, the original function must be bijective, right? And vice versa. It's an if and only if, right? So if you're bijective, then your inverse is a function. If your inverse is a function, then you're bijective. Either way, it holds true. Yeah, it's a great question, David. Does anyone have further questions about that? Does that make sense? Alrighty. So let's do some examples. In fact, I think I have a few proofs to do here. Well, I have one about inverse functions here. Maybe we should do that. While we're on the topic. Okay. So I've got the inverse of C union D equals the inverse of C union the inverse of D. So does function inverse distribute over union is the question. Okay. So what am I going to do here? Okay, oh, Haruka has a question. If it isn't surjective, not subjective, but surjective. Surjective, right? It's not a function. No, that's not true. You can be a function, but not surjective. So for example, x squared is a function. So y equals x squared, that example you said, that is a function because it passes the vertical line test, but it's not surjective because there are no outputs that are negative. Right? There's no negative numbers in the codomain, so it's not surjective. Does that make sense, Haruka? Does that answer your question? Sure, great. Okay, so for this proof, let me get you started. So let's have some element x, which is in the function inverse of C union D. Okay, well, that's only true if what? If f of x is an element of C union D. Let's think about that for a minute, right? What did I do? I applied an f to both sides of the equation, right? I took this set and applied the function f to it, and any function applied with its inverse, they cancel each other out, right? It's like adding 1 and subtracting 1. So on the right side, I just get C union D. And then on the left, I've applied the function, right? You can also, instead of thinking about this algebraically, you can think about it in terms of the definitions. If I have some x that's inside the f inverse of C union D, right? That means that f of x came from somewhere inside of C union D. Let's make a picture. Okay, so here's X, here's Y, here's C, and here's D. Right? Those are two sets, possibly with some overlap, inside of the codomain. And what I'm wondering about is the inverse image of C union D, right? So I'm wondering about, hey, you know, if I have some element here, right, that's f of x, that means that that came from some x over here. And where does that x live? Well, if x is inside of the inverse image of C union D, right? If that x is inside of there, that means that f of x, right, by definition, must come from C union D over on the codomain side. What do you guys think? Does that make sense? Okay. So what does this mean? Well, this means f of x is an element of C, or f of x is an element of D. Right? That's what union means. F of x could be in this one or in this one, right? And if f of x is in C, what can I say next? Good. Then x is an element of f inverse of C, or x is an element of f inverse of D. Wonderful. Last step. Conclude. X is an element of f inverse of C union f inverse of D. By definition of union. Union is just the or, right? And since these are all if and only ifs, these are all biconditionals, right? Then it goes both ways, right? X is an element of this, means it has to be an element of that. So the containment goes this way. And of course, the containment goes in the forward direction, right? And since it contains both ways, because of these bidirectional conditionals, then we have these two sets are equal. What do you guys think? Does that make you happy? Any questions? Is that the graded proof? Oh, did I just do the graded proof? Oh, crap. Uh-oh. I don't think so. I hope I didn't. Ah, no. So here, so let me show you the graded proof. Worried me for a second there. All right. Here's the proofs for this week. Oop. There they are. Okay. So if the composition of functions is bijective, then f is bijective. So that's something very different than the proof that I just did. It's in the same sort of spirit as the proof I just did. Like your proof method will be, you know, you could choose the same proof method that I just used, but it is actually a different proof. Does that make sense? Yeah, okay. You just misremembered it. Yeah, no problem. Okay. So for the graded proof, you can prove f doesn't need to be one-to-one. You can conclude that it doesn't need to be bijective. Yes, that's correct. That's exactly right, Nathan. if you can conclude that. And I forget which way it goes. You do either injective or surjective. I forget which one it is, but it won't be one of those things. So it's not bijective. I think that's the right approach. Yeah, Nathan, that's good. Okay, so let's try another one of these kinds of ones. Let's do an intersection one this time, right? Instead of a union. So here's what I've got. Is f of A intersect f of B equal to f of A intersect B? In other words, does the function distribute across intersection? Oh, the one I just did is on web work. Oh, okay, yeah. So this is one of the web work questions. Yeah. So here's how you would solve one of those true falses on the web work. That's what you were thinking of. Yep. Yeah. So here's how you would do like a formal proof of one of those web work things. Okay. So what about this one? Any thoughts on how to proceed here? Well, we could do that if we're trying to do an element style proof, but I don't think we should do an element style proof here. Why? Not too long, no, different reason. It's the other way. I'm not sure what you mean by that, David. Can you say more? The other way around. Oh, you mean like I should have switched these things like this? I'm not sure. And we don't want a Venn diagram either. The reason why we want a different proof method here is because this is false. So if that's false, then what style of proof should we be using? A counterexample. And what style should our counterexample be? I could try to do a counterexample proof by elements or something like this. But what what would be the easiest way to do a counterexample? Okay, so not a Venn diagram, but an arrow diagram. Okay, so I've got my arrow diagram here. I've got A and B. And they intersect, right? And then I've got over here f of A and f of B. Here's f of A and f of B. Which look like this. And the question is the intersection of f of A and f of B, which is this guy, that thing is FA intersect FB. Is that the same thing as f of the intersection? Right? Does this thing, when coming across, sit right in here? And I claim the answer is no, right? So can you think of a counterexample? Well, then you're in trouble, right, Noel? Yeah. So these are hard, right? And you do have to think about them quite a bit in order to really understand what's going on, right? Whether that's actually writing out one of these proof by elements, or if you can come up with a counterexample, you don't know in advance which one to do. You just have to kind of try both and see if you can figure it out. Yeah. Yeah, there's no easy answer here. It's just dependent on the problem. Some problems are easy, some are hard. Yeah, it just depends. This one I would say is kind of medium. Yeah. No, it's a great question. It's just unfortunately the answer is no, there's not a good strategy. Yeah. Okay, so anyone think of a counterexample? Okay. So A is 1, 2, B is 1, 3. So let me get in here. So A has a 2, B has a 3, and they share a 1. And that's X with A and B. Okay. And then you want 2 maps to 2, 1 maps to 3, and 3 maps to 3. Okay, so you only have a 2 and a 3 in the codomain, is that right? Am I understanding you correctly there? Yep, okay. So we've got a 2 and a 3. Okay, 2 maps to 2, 1 maps to 3, and 3 maps to 3. Okay, nice. All right, so in that case, what would we have for all these different sets? Okay, so first of all, let's write some stuff down. So what's f of A? What subset of the codomain do you get if you map all the elements of A, which include 2 and 1? So if you map all the elements of A, what subset of the codomain do you get? 2, 3. Perfect. Okay, how about f of B? Just 3. Okay. So in that case, f of A intersect f of B equals what? Just 3. If I intersect these two things, the only thing that's in common is the 3. Okay, so how about A intersect B is f of what? So what's A intersect B? Oh, you have 2 being shared instead of 1. Oh, does that make a difference? Okay, so I might have to redraw. But you think this works as well? Okay, so it works either way. Okay, good. So I don't have to redraw. Nice. Okay, so what's A intersect B? So I'm just going to substitute inside of here. Oh, works as in is not a counterexample. Okay. So then this would be 1, set 1, and f of the set 1 is 3. So it's not a counterexample. Okay. Yep, I see what you're saying. So we do have to redraw. Okay, so this is wrong. Let's try again. We've got 1, 2, and 3 inside of 2 sets, A and B, which all takes place in the domain X, which maps over to the codomain. 1 and 3 map to 3, and 2 maps to 2. So did I do it correctly this time, Lucas? Is that right? I think so. Okay, so let's try one more time. So we got f of A. F of A is how much? Or which things? So take all the elements of A, and what do they map to? 2, 3. So same as before, 2, 3. Okay, how about f of B? Oops, that's just a regular paren. Also 2 and 3, right? B, 2 and 3 map across to 2 and 3. Like this. Whoop. Okay, so f of A intersect B, or f of A intersect f of B would be what? Two, 3, perfect. Because it's the same in both cases. So there's a 2 and a 3. Okay, how about A intersect B equals what? Set 2, singleton set 2, and f of singleton 2 equals what? Just singleton 2. And now these are not equal. Two, 3 is not equal to 2. Good. Yeah, that's great. You found the counterexample. Very nice. Any questions there? Does that look good? Okay, very nice. So let's see if we can finish out this last section. I don't know if we can finish it, but we can come close at least. It's all about composition. So the composition of functions means applying multiple functions at once. So let f be a function from x to y, and g be a function from y to z. Careful to make a capital Z that's not this one. That's integers, right? This is not the same as capital set Z, right? Okay, so we've got f and g. Oh, crap, I did it wrong. Sorry. My brain's not all together today. Okay, there we go. G goes from y to z. Then G composed with F goes from X to Z where G composed with F of X equals g of f of x. And that's true for all x in x. So you're just nesting functions. That's pretty much it, right? Well, what if we wanted to make an arrow diagram of this, right? Well, we would have 3 circles now. We'd have x, y, and z, where f goes from x to y, g goes from y to z, and if we had some x in here, that's going to map over to f of x, and that's going to map over to g of f of x. What do you guys think? Look good? Questions? Okay, a couple of notes. So first off, let I of x be the identity function. I guess I should say I of x equals x, be the identity function, right? So it's a function where you plug something in, it gives you out the same answer, right? Well, what if I compose a function with the identity? F composed with I of x. What's that going to be equal to? Excuse me. Just f, right? It's just equal to f of x. And you could have done that in the other order if you want. It doesn't really matter which way. I could have also said I composed with f of x. Right? So if you compose the identity function with any other function, you just get that original function. Great. Well, what if I do this? What if I say, okay, well, what if I compose a function with its inverse? Turns out it doesn't matter which order you do that either, right? So I can also say f inverse of f of x equals the identity function of x, which is just x. That's true sometimes, but not all the time. When would this be true? And when would this not be true? This one's true all the time. This is always true. And this is true when f is bijective. Very good. I just say bij, bijective, right? Do that for short. Only when f is bijective. Why wouldn't it be true if f was not bijective? Like, what would go wrong? So if f is not bijective, yeah, then the inverse would not be a function, right? The inverse, you could say that it exists, I guess. I mean, you could still have the inverse of the function, but it wouldn't be well defined for all of the inputs. Yeah, there'd be like multiple x's giving the same, give the same x giving multiple outputs. Or I guess if you're talking about the inverse, it would be the same output gives you back multiple inputs, which is not a function. Yeah, excellent. Very good. Okay. Okay, a few more theorems here. I won't go through and prove these, but I will mention them to you. If f and g are both 1-to-1, then f composed with g is also 1-to-1. Similarly, if f and g are both onto, then f composed with g is also onto. And I'll let you look through the proofs for that in your book. They're relatively straightforward, so I think you guys can read through those. And we are out of time. So, okay. And I think that's all I wanted to do. So if you guys would read through the proofs of these in your book, that would be great. And we will jump into section 7.4 on Wednesday. We'll spend quite a while on that, and then we'll jump into the lab as well on Wednesday. Does anyone have any questions for me before we go? Yeah, you're very welcome. Okay, well, have a good one, everybody, and I'll see you Wednesday. Bye, guys.